We all know AI is getting smarter, right? I mean, you see these incredible images generated online, or you interact with chatbots that seem almost human.
Oh, absolutely. The capabilities are just exploding. They're phenomenal thinkers.
But here's something wild I read about, and maybe you can shed some light on this. The biggest speed bump for these amazing AIs,
Hmm.
it isn't actually how fast they think.
That's exactly right. It's not the raw calculation speed, not really. The major bottleneck, believe it or not, is how fast the AI can read its own memory.
Getting the data to the brain, essentially.
Precisely. We spend fortunes on faster chips, faster processors, but the performance limit often comes down to just moving data around.
Okay, so today let's do a deep dive into this. We're talking about high bandwidth memory, or HBM. It sounds like this is the tech that's trying to break down that barrier.
It is. HBM is specifically designed to smash what we call the memory wall. And it's a very real problem, especially for AI.
Tell me more about this memory wall. How big of a problem are we actually talking about?
Well, think about the kind of AI we use now. These huge neural networks, the models behind things like ChatGPT, they are fundamentally limited by memory bandwidth. Their performance hinges on how fast data moves, much more than raw compute power.
Okay. So, like, how does that gap look historically between the thinking speed and the data speed?
It's pretty stark if you look back, say, over the last couple of decades.
Yeah.
Peak computing power on server hardware, FLOPS, it roughly tripled every 2 years.
Okay, huge jumps.
Huge jumps. But traditional DRAM memory bandwidth, that only scaled up about 1.6 times in the same 2-year period.
Wow. Okay, so 3x versus 1.6x, that difference adds up fast.
It compounds massively. That growing gap is the memory wall. It's like having a Formula One engine connected to bicycle wheels.
That's a great analogy. So these super fast modern chips, they can't actually use all their speed.
Often, no. Take a top-tier GPU like NVIDIA's H100, for example. It might offer, say, a 6x jump in theoretical compute power over the previous generation.
6 times.
Yeah, incredible, right?
Yeah.
But the memory bandwidth it got, only about a 1.6x improvement, same slow scaling.
So what happens in practice? What's the real-world impact?
The consequence is inefficiency, big time. These cutting-edge, very expensive processors often operate at only maybe 60% of their potential utilization when running real AI tasks.
60%. So 40% of the time, they're just waiting.
Sitting idle, waiting for data to arrive from memory. That is the
Right.
cost of the memory wall. You might buy a, I don't know, $30,000 accelerator chip,
Yeah.
but because of the memory bottleneck, you might only be getting the effective performance of an $18,000 chip. The memory just can't keep up.
Okay, that's a huge financial hit. So the old way, this sort of flat, spread out memory design, like DDR memory, that's the
That's the suburb model, yeah.
Yeah.
Sprawling, flat, data has to travel relatively long distances.
An HBM solution is to build up, like a skyscraper.
Exactly. That skyscraper analogy is perfect. HBM's big innovation is its 3D stacked architecture. Instead of spreading memory chips out, it stacks multiple layers, multiple memory dies, vertically,
Okay, stacking them. How close are we talking?
right next to the processor, often on the same physical package, connected through something called an interposer. Extremely close.
And how do they connect those layers? You can't just stack chips, right? There must be connections through the silicon.
That's the magic, yeah. They use these tiny vertical connections called through-silicon vias, or TSVs. Think of them as microscopic pipes running vertically through the silicon layers.
How tiny are we talking?
Really tiny. The pitch, the spacing between them, is somewhere between 10 and 35 micrometers, thinner than a strand of spider silk. This lets them pack hundreds, even thousands of these vertical connections in a very small area.
Wow. So that density, that closeness, it slashes the distance data needs to travel.
Drastically. Shorter distance means lower latency, so faster access. And crucially, it means much lower power consumption to move each bit of data.
Less energy wasted just shuffling data back and forth.
Exactly. It's pushing towards this idea of a more unified system where compute and memory are almost intertwined, which is just what AI needs. Think about large language models, LLMs.
Yeah, they're huge.
They grew like 240 times in size in just 2 years. They need constant, massive, parallel access to billions of parameters. HBM gives them that by basically putting the pantry right next to the kitchen.
Okay, so the structure is key, but how does HBM actually achieve the speed? You mentioned it's not just about clocking it super fast.
Right, it's kind of counterintuitive. Traditional memory, like GDDR6 used in graphics cards, relies on very high clock speeds on a relatively narrow data path.
Like a really fast, but maybe only 2-lane highway.
Kind of, yeah. GDDR6 might use a 256-bit wide bus. HBM takes a totally different approach. It achieves its massive bandwidth through wide parallelism.
More lanes, not necessarily higher speed limit.
Exactly. HBM3, for instance, uses 16 independent 64-bit channels. You multiply that out.
16 times 64.
Yep.
That's 1,024 bits. A 1,024-bit wide interface per stack.
That's the one. A massive wide highway compared to the narrower GDDR path. And the next generation, HBM4, is set to double that to 2,048 bits with 32 channels.
2,000 bits wide. That's incredible parallelism. And this width, this is where the efficiency comes in.
That's the secret sauce for efficiency, yes. Let's put some numbers on it to get, say, 256 gigabytes per second of bandwidth.
Okay.
GDDR6 needs to run incredibly fast, something like 16 gigabits per second on each data pin.
Pretty demanding.
Very. Now, HBM2 could achieve that same 256 gigabits bandwidth running at only 2 gigabits per second per pin.
Wow, 8 times slower clock speed per pin for the same total bandwidth.
Exactly, because it has so many more pins, so many more lanes working in parallel.
Hmm.
And that lower speed per pin dramatically reduces power consumption.
Right, lower clock speed generally means less power needed.
And power efficiency is absolutely critical in data centers. They have enormous power bills and cooling challenges. HBM achieves something like 7 picojoules per bit in energy efficiency.
7 picojoules, how does that compare?
Well, some data suggests HBM can deliver 3 times the bandwidth of older GDDR5 memory while using only about 20% of the power.
20%. Okay, that 7 picojoules number isn't just abstract. That directly translates to lower operating costs, less heat. It's what makes running these gigantic AI models feasible, not just possible.
It's a crucial enabling factor, absolutely. It makes large-scale AI infrastructure more sustainable.
And you mentioned this wide parallelism is also just better suited for how AI actually works.
It maps very well, yes. AI models, especially neural networks, often process data in large batches, performing big matrix operations. HBM's wide independent channels let different parts of the AI accelerator grab different chunks of data simultaneously.
So the chip stays busy. It's not waiting as much.
Exactly. Maximizes that precious compute utilization. It's vital for handling the sheer scale. Modern LLMs, anything over maybe 7 billion parameters, needs tens of gigabytes, maybe 40 to 80 gigabytes or more, just to store the model weights.
Just the static model itself.
Right. And then you have the dynamic part, especially in generative AI. Like when you're chatting with an AI, there's something called the KV cache.
Okay, what's that?
It's basically the chatbot's memory of the current conversation, the context. As your conversation gets longer, or you feed it a huge document, that KV cache grows and grows.
Ah,
Yeah.
so the AI needs to constantly access the whole model plus this growing conversation history.
Precisely. With context windows now reaching tens, even hundreds of thousands of tokens, you need incredibly high sustained bandwidth to read all that data efficiently for every single word the AI generates. HBM provides that.
So the memory has to scale with the conversation length.
It does. And they're even adding tricks to make it better. There's a technique emerging called simultaneous multi-layer access, or SMLA.
Okay.
It essentially lets the chip grab data from multiple layers, multiple floors of the HBM skyscraper at the exact same time. It could boost bandwidth by up to 4x in some cases.
Wow, squeezing even more out of the stack. This sounds almost too good to be true. High speed, low power, perfect for AIs. There has to be a catch, right?
Oh, there's definitely a catch, or rather, several catches. Building these microscopic skyscrapers isn't easy or cheap, which brings us to the manufacturing reality.
Yeah, I was wondering about that. Stacking delicate silicon layers with thousands of tiny vertical connections sounds incredibly complex.
Yeah.
And probably hot.
Intensely complex, yes.
Right.
The manufacturing process for HBM involves roughly 19 additional, quite sophisticated materials engineering steps compared to standard DRAM, just for the 3D stacking part.
19 extra steps. That sounds expensive.
It is, and that cost shows up dramatically. HBM reportedly accounts for 50 to 60% of the total manufacturing cost of a high-end AI GPU.
Whoa, wait, 50 to 60%? Just for the memory?
So for the HBM stacks, yeah.
That's astounding. Like buying a performance car where the custom tires and suspension cost more than the engine itself.
It's a good comparison. It really highlights how critical and how expensive this component is. It's a huge factor in why those top AI accelerators cost tens of thousands of dollars.
And I imagine that complexity also impacts supply.
Absolutely. It's not easy to manufacture this stuff at scale and with good yields. Currently, there are really only 3 major players reliably producing HBM SK Hynix.
Okay.
They're the dominant one, maybe 60–70% market share, according to some reports. Then Samsung and Micron. That's pretty much it.
So limited competition, high demand from the AI boom that keeps prices high and supply tight.
That's the market reality, yes.
And what about the heat? You stack all these active layers together, generating heat.
Yeah.
How do you cool a skyscraper?
That's the other major challenge. Thermal management. You nailed it earlier. Concentrating all that activity vertically creates hotspots.
Yeah, heat rises, right? Does it get trapped?
It does. Heat dissipation becomes much harder in a tall stack.
Okay.
Sources point out that the thermal resistance, basically how hard it is for heat to escape, increases sharply once you go beyond about 12 layers high.
So you get these temperature gradients within the stack.
Exactly. Uneven heating, which can stress the connections, impact reliability, and potentially lead to new kinds of failures that you don't see in flatter memory designs.
So you solve the bandwidth bottleneck, but you run into a potential thermal ceiling. Yet the industry seems to be pushing forward regardless. What's the roadmap look like? What's coming next?
Well, the hunger for bandwidth isn't slowing down. The next standard, HBM4, is expected to be finalized by the standards body, JGS, in 2025.
And what does HBM4 bring? We mentioned double the interface width.
Yep, doubling again to that 2048-bit interface, and it's targeting bandwidth of up to 2 terabytes per second per stack.
2 terabytes a second per stack. That's hard to even comprehend.
It's astronomical speed, yeah. SK Hynix has already indicated they've completed development on their HBM4 product.
But beyond just faster, wider HBM, you mentioned something earlier that sounded even more radical. Processing and memory, PI.
Ah, yes. PIM is potentially the real game changer down the road. It's still an emerging architecture, but the idea is incredibly powerful.
What's the core concept?
Instead of just storing data, PIM integrates actual compute elements directly inside the HBM memory stack itself.
So the memory starts thinking.
In a way, yes. For certain types of simple, data-intensive operations common in AI, the memory could perform calculations locally, right where the data lives.
Avoiding the need to ship the data over to the main processor and back again.
Exactly. It drastically reduces that data movement overhead, which, as we've discussed, is a huge energy drain and performance bottleneck. It makes the memory itself smarter, more active.
That feels like a fundamental shift, and the market seems to be betting big on HBM in general.
Oh, absolutely. The projections are pretty wild. The global HBM market was valued around, what, $2.5 billion in 2024?
Seems reasonable.
But some forecasts, driven almost entirely by AI infrastructure build-out, predict it could explode to nearly $140 billion by 2031.
Wow, $140 billion. That's just massive growth. Betting that AI's appetite for bandwidth will only increase?
It seems like a safe bet right now.
Okay, so wrapping this deep dive up, it's really clear that memory isn't just this passive storage thing anymore, at least not for high-performance computing.
Not at all. It's moved from being a simple component to being arguably the central challenge and the critical lifeline for modern AI.
So if you, listening, were to take away just a few key things from our chat today, what should they be?
I'd say first, remember the memory wall. AI progress is often limited more by data movement speed than raw calculation speed. Powerful chips can end up underutilized, maybe running at only 60% capacity, just waiting for data.
Okay, the wall is real. Second point.
Second, HBM tackles this wall with 3D, stacking those vertical skyscrapers and ultra-wide parallelism. Think that massive 1024-bit highway. This gives huge bandwidth and amazing power efficiency, down around that 7 picojoules per bit mark.
Got it. Stat high, go wide, save power. And the third takeaway.
Third, while HBM is crucial for today's giant AI models, especially LLMs, it's not easy. The manufacturing complexity is immense, leading to high costs. Remember, 50–60% of a GPU's cost and significant thermal challenges. These are real limiting factors right now.
So connecting this to the bigger picture then, HBM isn't just a component upgrade. It feels like it's fundamentally changing how we design computers.
It really is. It's accelerating this trend towards tightly integrated, almost unified compute memory systems, breaking down the traditional separation.
Which leads to a really interesting thought to leave folks with.
Yeah, if you push this forward, with the complexity of making HBM and the promise of things like processing and memory, could we see future generations where compute and memory essentially merge?
Where the distinction just dissolves.
Right. What happens when the processor and its data source become one and the same? What does that kind of architecture mean for the future devices you own? What if the memory is the intelligence?